Alright, gang, we're going to talk about antiderivatives. This is the last section of the chapter, and it's going to be pretty rich in content. So these are some of the objectives that I'm going to try to cover here. This is kind of our intro into working backwards. So antiderivatives are not finding the derivatives, but we're finding the function that comes before it, that's the antiderivative of it. So it's kind of set up for integrals. They're not exactly the same thing, but same idea, working backwards. Okay? All right. First thing, little terminology. Sometimes we use the capital F of x to mean that it's the antiderivative of f, meaning that if we were to take the derivative of the capital F of x, then that would actually be little f of x. So sometimes we do it this way with the capitals. All right, so knowing that, let's say we start off with this function, f of x equals x squared. Let's try to come up with the antiderivative. So we're trying to think of the function that if we took the derivative of it, it would actually give us x squared. So it's kind of different, us working backwards a little bit. So what do you guys think? Because we know if we take the derivative of this, let's see, we know that, how we take the derivative of it, we kind of we lose a little bit of the power. So some people think, maybe if we say it would be capital, maybe if we say it would be capital F of x, let's say that would be x cubed. That wouldn't quite work, because then if we take the derivative, d of x cubed, then it would be 3x squared, and we want it to be just x squared. So what we'd have to do is we'd have to figure out a way to get rid of that 3, and so it turns out that we need to divide by 3. So actually the perfect antiderivative for this function is capital F of x, and it would be x cubed, and we'd have to divide that by 3, and then it'd be perfect. So if we took the derivative of this capital F of x, then we would of course carry the 1/3, we'd bring the 3 out in front, and that would cancel out with the 1/3, and then we would reduce that by 1, and so then we would get, exactly x squared. So this would work. Just make a note. All right. If we graph this, so let's say we graph this particular antiderivative, it would be just a normal cubic, just go right through the origin. So it's this one right here. And what if we kept, what if we shifted this particular function kind of up and down on the graph? Would that really make any kind of a difference to the derivative? So let's say we added, I have over here, the different things, if I added 2 to it, I'd get this graph, it just shifts it up and down. Or if I shifted it up, maybe 5 units, then I would get this graph. But you remember when we take the derivative of this, if I had like a plus 5 or something, if I took the derivative of this, wouldn't we just lose the constant anyways? So it wouldn't really affect anything. And so whenever we're finding derivatives, or antiderivatives, what we'll do is we'll say, hey, you know what? Whenever we're finding the derivatives, the whole shifting doesn't really change anything. So what we're going to do is we're going to have this arbitrary c every time we find the antiderivative. We're going to have this arbitrary constant, because we're saying, hey, it's possible when we find the antiderivative that it's going to have some constant here, and we don't necessarily know what it's going to be, so we're just going to leave it this generic c. Unless somebody tells us a little initial information, then we'll be able to nail down exactly what the antiderivative is if we know that it goes through a particular point. But if we don't know, a certain point that it goes through, then it's going to be one answer of many. Okay. All right. Here's a table of antiderivatives that I need to give you. We'll have to memorize this. So this side here, of course, with the little f of x is the actual derivative, and then this side is the antiderivative. So whenever you have a constant with a function, you know, all you do is you just carry the constant right along for the ride. You know when you take the derivative, that's the case. So antiderivative, exactly the case. And we know if we were finding the antiderivative and there's a plus sign in the middle, then that won't really change anything. So we still just find the antiderivative and we use a plus sign in the middle. So no big deal there. Now here's the one that we kind of looked at just now. And whenever you have x raised to some power, what you do is you just add 1 to it, and then you divide by that same amount. So if it's x to the n, then we just add 1 to it, and then we divide by n plus 1. You divide by that same amount. So it's just the opposite of the power rule. Okay? Now this one right here is 1 over x, and that is a special type, because really that's x to the negative 1, and we cannot add 1 to that and divide, because if we add 1 to that, then we would have x to the 0, and that would be, you know, that would equal 1, and that's just not what the antiderivative is. So, because then if we took the derivative of that, then it would be 0, and that isn't what 1 over x is. So, the antiderivative of this, can you think of a derivative that actually gives us 1 over x? Well, you might remember that that's natural log. So it's natural log, and it's actually natural log of the absolute value of x. And what that does is that just makes sure that the domain is, you know, is what it needs to be. It needs to be positive, so that guarantees it. The derivative of the antiderivative of e to the x, you might guess this one. It's exactly the same, because we know when you take the derivative, it's e to the x, so it makes sense when you work the other way. And then we know the derivative of cosine is negative sine x, but when you're going backwards, you have to think about what function, when you take the derivative of it, does it give you cosine x? And so you might remember that that would be sine x. So if I took the derivative of sine x, I would get cosine x, so that's why that's the antiderivative. A couple more. If I take the derivative of some function, what function would that be? If I knew the derivative was sine x, well, that would be cosine x. How about secant squared? Can you think of a function that, you know, if you took the derivative of it, you would actually get secant squared? So you might be getting the idea here. So yeah, that function would be tangent. So the antiderivative of secant squared is tangent. Can you think of a derivative that, when you find it, it gives you secant x tangent x? Well, that means the antiderivative would be secant x. Sorry, hold on. And then you might remember your inverse trig derivatives a little bit. So the one that goes with this is the inverse sine of x. And then remember this one, 1 over 1 plus x squared. You might remember that this is inverse tangent x. So that's your list that you want to commit to memory. All right, let's do an example. So we start off with a particular derivative, and we want a function, let's just say, and we want to find the antiderivative. So all you do is say, hey, I'm finding the antiderivative. So you put a big capital F of x, if it just gives you f of x. And then what you're going to do is you're going to write 6, you're carrying the constant along for the ride, and then you raise this up 1, and then divide by that same amount. And then with the 8, you just carry it along for the ride. And then with the x, you raise the power, so you raise it by 1, and then divide by that same amount. And then whenever you have a constant, you just give it an x. So it's going to be 3x. Remember how that works? If you have 3x and you find the derivative, then it just becomes a constant. So think about that backwards. And then if you don't have any initial information, then you're going to say plus c. All right, and then you could leave it like that, or do a little bit of simplifying, clean it up. So that will cancel out. So this would be 2x cubed. Wow, I might have to change my battery real quick. So minus, and then 4x squared. Sorry about that. And then plus 3x. Wow. plus c. So that would be your most general antiderivative. Now, is there a way to check that? Well, yeah, you could take the derivative of it. So go ahead and just use the power rule and take the derivative of that. So you can see that would be 3 times 2, so that would be 6, and then reduce it by a power, so that would be 6x squared, and you can do the rest of it and see if that would work out. All right. Next example. What about if they give you a little bit of initial conditions? So they say, hey, f prime of x equals this function, and by the way, we're letting you know that it actually goes through this particular point. All right. Well, the notation is a little bit different because they're giving us f prime of x. So that means that the antiderivative of this is f of x. So we're going to say f of x equals, and we're going to do the same exact thing. So we're going to say 8, and we're going to say x to the 4th divided by 4 plus 12. We're going to add 1, so we're going to divide by that same number, and then plus 3x, and then plus this arbitrary c. So let me do a little cleanup before I plug in the point that they give us. So that would be 2x to the 4th plus 6x squared plus 3x plus c. Now that's the best we could do unless they give you a little bit of initial information, and they do. And so they tell us that f of 1 equals 6. So we're just going to plug in a 6 for the y, and we're going to plug in a 1 everywhere else. Right. And we should be able to nail down what the c is. So show the work on that, and if you solve this for c, I bet you can do that. So c would equal -5. And so that helps us write the exact function for this. And so the exact function is f of x equals, the same thing. So 2x to the 4th plus 6x squared plus 3x. And so we no longer have this arbitrary constant. We know exactly what it is. It's -5 because we had some initial conditions to be able to nail down exactly what the antiderivative is. Okay? Final answer, same thing there. All right, now you might have a second derivative, so it's not really that much different. You just have to do it twice. So we know the antiderivative of f double prime is f single prime, so we would say f prime of x equals, and then we would say, okay, we're going to add 1 to that, so x cubed divided by 3 plus, and then 3, and then we got to think about the antiderivative of that, so that would be sine x, and then we have this plus c, and then we would utilize the information. So here's the information we would use. It says that whenever you plug in a 0 to f prime, you get a 3. So that means we would be able to plug in a 3 right here. And we'd plug in a 0 everywhere else. So that would be 0. And then actually that would be 3 sine. That would be 3 sine 0 plus c. And if we solve that for c, then c would equal 3. So that helps us. We can figure out now exactly what the f prime is. So f prime of x is equal to, sorry, I'm struggling a little bit with this, 1. So that means we're going to have x cubed over 3 plus 3 sine x, and then we figured out that it's 3, so that would be plus 3. And then now we can just do it once more to figure out the initial function. So we're going to say f prime of x, oops, just kidding, now we're going to say f of x. So f of x is equal to, and now we would carry the 1/3, and we would raise this up by 1 power. So that would be x to the 4, and then we divide by 4, and then plus, and then 3. And then we'd have to figure out, what the antiderivative of that is. So that would be minus cosine x, and then plus 3x, and then plus c. And then we would use the information given, and we can see that we have initial information that when we plug in a 0, we get a 2. So that means I'm going to go to the next slide, but I'm going to plug in a 2 to this side, and I'm going to plug in a 0 everywhere where there's an x. Okay. So that would be, whoops, get back, add a page. Okay, so if I did that, then I would have 2 on the left-hand side, and then I would have, well, it would be 1/12, but then, times 0 to the 4th, and then plus -3 times cosine of 0, and then plus 3 times 0, and then plus c. So doing a little bit of calculations there, that becomes 0. This actually becomes -3 because cosine 0 is 1. So we get -3 plus c equals 2. So we add the 3 over, so c turns out to be 5. So now we've nailed down exactly what our function is. Our function is f of x. Wow, that's going to be a lot of trouble. So our function is f of x equals 1/12 x to the 4 minus 3 cosine x plus 3x plus 5. Okay? Alright, let's see what we got here. Okay. This is an application. These are the ones that are amazing to me, that you can actually come up with the function to describe this. So we have a ball that's thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground, and we want to answer these questions. So I'll let you kind of pause it to get the questions. But the first thing we know is we actually know the acceleration. So this is working backwards. So we know the acceleration due to gravity. So we know the acceleration of gravity is one of two things. It depends on if you're doing meters per second squared or if you're using feet per second squared. So it's negative, and it's a negative acceleration. So it's negative 9.8 meters per second squared, or, depending on the problem, it could be negative 32 feet per second squared. All right, so what we know to start this off is we know that the acceleration as a function of time for this ball going up is definitely negative 32, and that's going to be true for all objects. So negative 32. And we know that whenever we have the acceleration function, if we ever wanted to find the velocity function, then we just find the antiderivative. So v of t equals, and we just find the antiderivative of this, which is negative 32 t. So we'd say negative 32 t, okay? And then we'd have a plus c, so we still have that arbitrary constant. But I think they gave us a little information, and they said that, hey, we know the initial velocity. The initial velocity was 48 feet per second. So they told us that v sub 0 at 0 time, that the velocity was actually 48 feet per second. So we can use that. We can nail down exactly what the velocity function is. So we could plug in 48, to the left-hand side. We can actually just plug it in for the c, but I'm going to show the work. So negative 32 times 0 plus c. Turns out that c is 48. And that would always be the case. I mean, pretty much whenever it's v of 0, that you could probably just put the 48 right there for the c. So I'm going to go ahead and write what the b of t is. So our velocity function is equal to negative 32t, and now we know it's plus 48. Well, if you want to find the position function, then you just have to find the antiderivative of velocity. So that's usually s of t. So s of t equals, and we would just find the antiderivative of that. So that would be negative 32, and then it would be t squared divided by 2 plus 48t plus some arbitrary constant. Well, I think they told us the position of the ball at 0 time. They said that s of 0 was at the top of the cliff, so the position was actually 432 feet. So we can actually nail down exactly what the initial position is. And just for the sake of time, I'm going to say that if I was to plug in a 0 for both of those t's, that's what I would end up putting as get my c for 432. That's what I would get if I actually plugged in 432 right here and then I plugged in a 0 there. So for the sake of time, I'm going to say that s of t, to nail down exactly what this function is, it's negative 16t squared plus 48t, and then plus the 432. And I think this is the coolest thing because you can actually come up with a function just based upon a little bit of information. And it also shows you kind of where that negative 16 is coming from whenever you do these application problems. So let's just quickly answer the last couple questions and call it good for this one. All right, so one of the questions, part B, this is all part A. Part B, it said, what was the, let me go back and make sure. It said, when does it reach the maximum height? So now that you have the function, it would be really, pretty easy. You can just graph it on your calculator and see what the maximum height is. And it's just something like this, and then you would just find that spot, and that's at 1.5 seconds. Use your calculator, 1.5 seconds, it's 468 feet. So you can check that out. And then part C, it said something like, what did it say? It said, when does it hit the ground? Well, it hits the ground when it has, 0 position there. So all you have to do is figure out the 0 function. So you just would look right here, see where it crosses when it has the position of 0, and that's at 6.90 seconds. So that's when it hits the ground. Okay? So I think I'm going to call it good because that's 23 minutes. I do have a couple more things to show you, but I'll do a part 2. Let me see. Actually, let me do a tiny bit more. All right, sketch the antiderivative. So here's a problem, and this is f of x right here, and they're wanting us to see if we could sketch the antiderivative. Well, again, this is really working backwards. So the way I do this is I typically start with the point that they give us. Sometimes they'll give us that point, and so I'll go ahead and plot that point. So 0, 2. Okay. Then what I do is I look over to the left, and I can see that when x is a little bit to the left of 0, my derivative, remember this is the derivative of the graph, so this is describing the slopes of the tangent lines of this graph over on the right. So it looks like my slopes, it's below the x-axis, so it's negative. So that means that my slopes are negative, and so it's probably going to look, something like this. And then I know that right here at negative 2, it has a slope of 0. So that means at negative 2, it somehow levels out right here at x equals negative 2. Again, it's corresponding to this point. And then also notice that to the left of negative 2, it's above the x-axis. That means that my original function actually has a positive slope. So it actually goes like this. So that's a rough sketch of what's going on there so far. Again, again, it kind of levels out right there at -2. Now, working the other side, if I look right here, I could see that it's still a negative slope, but it is getting closer to 0. So I have a negative slope, and then, so I would go ahead and sketch this. I have a negative slope still. And then notice that at this spot, I should have a leveling out of my initial function. So it would go down, this is very rough, but whenever x equals 2, the spot, it says that the slope of the tangent line is 0, so that means that this levels out right here at 2. And then notice, when you look at this graph, this is all positive then. So at 2, it actually starts having a positive slope. So then it would go up something like this. This would be a rough sketch of the antiderivative if f of x is the derivative. And again, kind of think about this. The one on the right starts off as a cubic, and then if you took the derivative, you get something that's quadratic or a parabola. So I think I'm going to call it there, and then we'll do the rest in class. All right, cool.